So we will be integrating this equation using integration by parts. The equation we will be using is the integral of u dv is equal to u times v minus the integral of v du. So in order for us to apply this equation, I would need to choose what my u function is and what my dv function is going to be. So here I'm going to choose u to be t squared, and dv is whatever is left inside the integral, which is et dt. So here as well, I would need to obtain a du, and I would obtain that by taking the derivative of the u function. So I would get 2t dt, and I would also need to obtain a v function, and I would obtain that by taking the integral of dv, and here we would get e to the t. So now inputting this into the equation, u times v is t squared times et minus the integral of v, which is et, times 2t times dt. So now here we know that any constant inside the integral we can just pull out. So I will be pulling out the 2. And also notice that multiplication is commutative, so I can rewrite this function after pulling out the 2 as et. So here I can still not integrate this integral right here because it's an unfamiliar integral, so I would have to apply the integration by parts again. So here I'm going to do some side work, and I'm going to set again u equal to and dv. Here my u is going to be the function t, dv what's ever left inside the integral, which is et dt. So now du here is going to be dt, and v is going to be e to the t. Now here reapplying the equation right here, u times v is t times et minus the integral of v, which is et, times du, which is dt. Now here, e to the t is an integral. We are familiar with integrating, so we would obtain here 2t minus et plus c. Now this is not our final answer because whatever we obtained here is just the integral of this part right here. So now putting these together as our answer, we would obtain the first part of the first integral, which is t squared et minus 2. And now I'm going to open a parentheses, and whatever I obtained from the second integral is going to go here. So t et minus et plus c. Now this is our answer, but we can also as well just distribute it the 2, and we can obtain t squared et minus 2t et plus 2et minus 2c. Now some people right here just like to put this 2c into like just as a plus c. So we could just say that c2 is equal to negative 2c, and we can rewrite our final answer as t squared et minus 2t et plus 2et plus c2. Now the 2 right here, the subscript 2, just shows that we applied the integration by parts twice. So here we will be using the integration by part equation. Again, the same equation we used in example 1. I'm going to let my u equal e to the x, my dv equals sine of x dx, du going to be the derivative of u, which is e to the x dx. V is going to be the integral of dv, which is negative cosine of x. The reason it's negative cosine of x because the derivative of cosine of x is negative sine of x, but here our dv is a positive sine of x. So to fix that, we just multiply the integral by a negative, and then whenever we take the derivative of negative cosine of x, we'll be able to obtain sine of x. Now putting the equation together, it's u times v e to the x times negative cosine of x minus the integral of v, which is negative cosine of x times du e to the x dx. Now here, since multiplication is commutative, I can rewrite this function as negative e to the x cosine of x, and any constant inside the integral I can just pull out. So I will pull out the negative to the outside, giving me plus the integral of e to the x cosine of x dx. Now here I have to reapply the integration by parts again into this equation. And doing some side work, I'm going to let my u equal e to the x. My dv is equal to cosine of x dx. Now here my du is equal to e to the x dx. And my v is going to equal sine of x. Putting it into the equation, u times v is e to the x times sine of x minus the integral of v, which is sine x, e to the x dx. Now notice that this integral right here is the same integral we started with at the beginning. So in this situation, we are first going to rewrite our solution. So taking this part right here, I will have my equation, the integral of e to the x sine of x dx is equal to negative e to the x cosine of x plus, now I open a parenthesis, and whatever I obtain from the second integration by parts I will put here, which is e to the x sine of x minus the integral of sine x ex dx. Distributing the plus to the integral, I would obtain the integral of ex sine of x dx equal to negative ex cosine of x plus e to the x sine of x minus the integral of sine of x ex dx. Now this right here, since I obtained the same integral I started with, no matter how many times I apply the integration by parts, I will end up with this integral. So right here, we will use some math tricks to solve this problem. Since this is the same integral we started with, I can add this integral to both sides. So when you add this integral to both sides of the equation, you would obtain 2 integral of e to the x sine of x dx is equal to, now here it cancels out from the other side, negative e to the x cosine of x plus e to the x sine of x. Now here I need to solve for the integral of e to the x sine of x dx. Since I have this 2 in front of the integral, in order to obtain the solution I'm looking for, all I have to do is just divide that 2 to both sides, and then I would end up with my final solution, the integral of e to the x sine of x dx is equal to negative e to the x cosine of x plus e to the x sine of x all over 2. And then don't forget the plus c at the end. All right, so now right here we have the integral from 0 to 1 tan inverse of x dx. So the way we apply here the integration by parts again is we're going to set our u to equal tan inverse of x. Now here, remember, our dv is always going to be whatever left inside of the integral. Now in this problem, when we solve it, we are going to ignore the conditions as of now, and then we'll come back to them towards the end. So here my dv is whatever left inside of the integral, and whatever is left inside of the integral is basically dx. Now obtaining du, the derivative of tan inverse is 1 over x squared plus 1 dx. V is just going to be whatever we have a integral of dx, is there's a 1 in front of it, so that only obtains the variable x. Now inputting that into the integration by parts equation, u times v gives you tan inverse of x times x minus the integral of v, which is x, times du 1 over x squared plus 1 dx. I'm gonna rewrite this as x times tan inverse of x minus, I'm gonna multiply x by the fraction, which obtains x over x squared plus 1 dx. Now here, I don't need to apply integration by parts, because by looking at this function right here, I know that I can use the u substitution, because if I allow my u to be x squared plus 1, I do have the derivative of that, which is 2x, which I only care about the variable x. So here I will actually use the u substitution. So using the u substitution for this part right here, u sub, I'm gonna let my u equal whatever is underneath the fraction in the denominator, which is x squared plus 1. My du is gonna be the derivative of u, which is 2x dx. Now here, I notice that I have the x that's being multiplied by the dx, but I do not have the 2. So to fix that problem, I will just divide the 2 to both sides, and I will obtain du over 2 is equal to x dx. Now here, I will rewrite the equation. I will do the u substitution right here. I will take the derivative, the integral of this. So I would have 1 over u and then du over 2. I can pull out the 2 on the bottom as 1/2 1 over u du. Now the integral of 1 over u, we know it's the log function ln. So ln of u. Now inputting that into the place of the integral, my final answer is going to be x tan inverse of x minus whatever I obtain from integration, which is 1/2 ln. Now instead of u, I want to obtain the function back in terms of x. So I know that u is x squared plus 1. Now I don't need here plus c, because I do have the condition that I'm going to apply, which is from 0 to 1. So now here, for every x, I am going to input 1, and then I will subtract the function again, but for instead of x, I will put 0. So here we would have 1 times tan inverse of 1 minus 1/2 ln of 1 squared plus 1. So this will give me tan inverse of 1 minus 1/2 ln of 2. Now I'm going to do the same thing, but I'm going to input 0 for every function of x. Now here, when I input x equals 0, notice I will have 0 times tan inverse of 0 minus 1/2 ln of 0 squared plus 1. Now, since this function is being multiplied by 0, I would obtain 0. Here, I would have 0 plus 1, which is 1. ln of 1 is 0, so it's 0. So since the outcome here is 0, I really don't need to care about the 0 on the bottom. Now here, my final answer is going to be tan inverse of 1 minus 1/2 ln of 2. So here, tan inverse of 1, if you go over the unit circle, you know that you'll obtain pi over 4 minus 1/2 ln of 2. And that would be the final answer.